Hello everybody, and welcome to the first in a series of review videos covering common conservation equations used in mechanical engineering. I am Professor Matt Anderson, and I'm excited to be leading us on this review video. Keep in mind that these videos were developed as a refresher for thermal science conservation equations that were previously introduced in your core ME courses. As such, they are not a complete introduction to the principles previously presented and derived in your core intro classes. This is the first of 4 videos covering conservation of mass, also referred to as mass balance or continuity. So without any further ado, let's jump right in. Based on the principle that mass can neither be created nor destroyed, in engineering we use a couple of equations that we call our mass balance equations. These equations I will shorthand as just mass balance in our notes or our examples as we're working our way through. Applying these equations, we need to define a system or a region that we're interested in. And so in engineering, we commonly look at different devices or engines. So let me quickly draw an engine that we might be interested in. When analyzing a gas turbine, as I have drawn here in a cartoon representation, we have to define the region that we're interested in looking at. And so we've done that in the past using red dashed lines. So if I'm interested in analyzing the whole engine, I say I put my blinders on and I look at something that's bounded. This is a region that we call a control volume. This control volume is differentiated the internal parts that I'm interested in analyzing versus the external environment. The control surface is this red dashed line that I've drawn here that differentiates the internal system or control volume from our environment. We could, if we were interested in looking at just a single component of this engine, say the compressor, analyze something like this. Right? All of these are possible, and it all depends on what we're trying to analyze or design. Looking at whatever system we might be interested in, we've previously defined and started in our thermal classes analyzing these things from a lumped analysis. So this lumped analysis, the equation that we used, looked something like this, where the first term here is the time rate of change of mass, capital M, inside of our control volume. That must be balanced by the difference in mass flow rate in or out. If we have the same mass flow rate in as we have coming out, we're in equilibrium or steady state, we call it. Let's recall again that this mass, m dot, is actually defined as the integral over an area that we're interested in of the density of that fluid times the velocity, again, integrated over that area. Right? So if we have multiple inlets and outlets, say we have location 1 where we have flow coming in, and we have location 2 where we have flow coming out, we can analyze this system according to this mass balance that we have previously derived. Moving on from our lump form of the equation, we can take a look at the integral form, which is the exact same thing, right? It's just a conservation of mass. The first term in this equation here is our time rate of change of mass within the control volume, and that term must be balanced by the flow of mass crossing our control surface or our system boundary, right? So this first term, you'll notice that it is an integral over a volume, so that dv term has a line through it. That's my notation for a volume to differentiate it from a velocity. We could probably think of this as a triple integral, right? And then this second term here is an integral over space here, so that could be a double integral. But for the sake of cleanliness, let's remove those. The last point to bring up in this equation here, in this form of the mass balance equation, is to look at the second term. Previously in our lumped equation, we had a mass flow rate in term that was different from our mass flow rate out term. Now both of these terms are encompassed in this one integral. If we recall, looking at our control surface, so I'm just going to draw a portion of it, where we have our control volume on the inside, and out here is the environment or surroundings that we call it. Commonly, the normal vector points outward. So the normal vector is a unit vector pointing outward on the surface of our control surface. If our velocity, we can take a different color here, is going in this direction, this is our velocity vector. If that's going in the outward side, so our dot product of our normal vector and our velocity is positive, that's going to be a mass flow rate out of our system. As opposed to, if our velocity term is going into our control volume, now the dot product of those two vectors turns out to be a negative term. So now both inflow and outflow is all encompassing in that one integral term. The final point I'd like to bring up is let's take our control volume and let's write it in Cartesian coordinates and make it differentially small. So let me just quick draw that. So now if we take this control volume and we apply our conservation equation to it, we will be able to write up, and we'll see what we drove in our fluid mechanics class, or again in your first transport class. This is the continuity equation, which is one of the equations in the Navier-Stokes equation. Let me draw a couple of velocity vectors just so we have terminology the same, right? And so let's say that we have our Cartesian coordinate system, which is defined by x, y, and according to our right-hand rule, z. We know that any chunk of fluid, if we look at that region right there, could have a velocity. That velocity is a vector, right? And so what I'm going to do here is I'm going to draw the three different components of this velocity and write their and what we commonly call them. So if we take a look at the x component of velocity, right, we usually call that u. The y component of velocity is v, and we'll write that as lowercase v, and the z component of velocity is commonly w. Our three Cartesian coordinates, the three directions x, y, and z, have unit vectors, and we will write those as I hat, sneak a j hat in there, and a k hat. And so now we can write our velocity, which is a vector, in terms of its three Cartesian components. So let me clean up the board and write that out. Our velocity vector can be written as the sum of all three of those components, u in the x direction, the component of velocity in the y direction, plus the component of velocity in the z direction. Last thing, if we take a couple of simplifications, the most common one is let's look at incompressible fluids. So if it's incompressible, our density doesn't change. Rho is equal to a constant. If that is the case, we can write this in terms of a vector equation. So this is the divergence of our velocity vector must be equal to 0. Or if you wrote this or you saw this again, you can write it in Einstein notation, right? Which says the exact same thing in just a more shorthand version. I know that was a lot, but I think we got through a review of conservation of mass in both a lumped equation sense as well as in our integral sense, and we even expanded that down to the Navier-Stokes equation, or our continuity equation, in a differential form. With that, I'm going to conclude this review video of the conservation of mass. Hopefully you found this useful, and as always, if you have any questions, please feel free to reach out to myself or the TAs.